Good afternoon. I'm really pleased to welcome you to this session of the conference, the parallel session on structural materials. And our first speaker is Katerina Ioannidou, who is an invited speaker. And Katerina is joining us from the Laboratory of Mechanics and Civil Engineering at the University of Montpellier, where she's been based for the past 3 years. Prior to joining the team at Montpellier, Katerina did a PhD in physics at NKUA in Athens in Greece. She then did an MSc in theoretical physics in Utrecht and a PhD in material science in ETH Zurich. And before Katerina moved to CNRS in Montpellier, she was working in MIT on the Concrete Sustainability Hub. And I have, since I became aware of her work, I found what Katerina is doing really interesting because she's applying very fundamental modeling to look at materials in civil engineering. And that's certainly very, very much needed in this discipline. So I'll pass you over to Katerina now, and we should have some time for questions afterwards.
Okay, thank you very much, Catherine, for the introduction. I hope you're all hearing me well, otherwise make a sign. So I'm going to try to give you some examples of coarse-grained modeling that we have been doing for understanding cement hydrates. So I will start a little bit with motivation. So here you can see some nice structures of done with cement. So on the left, we have Pantheon. It's one of the largest unreinforced domes that we have on the world, and it's something that we cannot do anymore. We have lost the technology to use unreinforced concrete. Of course, we're using reinforced concrete, and we can make bridges, as you see here, or aesthetically nice museums, as the museum in Marseille. But apart of seeing how nice cement is, it's also a very important material in our society. I'd like to show usually this infographic that can give us an information of how much cement we consume all over the world. For example, here you can see that China the past 3 years has used more cement than US used the past century. And given the urbanization and the population growth, these numbers are only foreseen to increase. So basically, cement is one of the materials that we produce and use the most. So it's actually the second most consumed material after water on the world. So many of you might think that cement, because it's such a conventional material and it's all around us, we have figured it out very well. So what's happening with it? So actually, this is not the case. And this is what I'm trying to show in this slide here, where I'm trying to get you through the different scales of cement and concrete. It's a very multi-scale material. Actually, we can make a little separation of the two words, cement and concrete, for people who are not familiar with this. So basically, concrete is the agglomeration of different aggregates of different stones or sand, which are glued together with a binder, and the binder is the cement. So basically, we are taking the cement, which is a reactive powder, and when we mix it with water, we have a hydration reaction that is forming a solid material. So we're starting from a liquid, from a suspension, and after a few hours, we have a solid material that glues together fine or coarser aggregates, and we have concrete. If we start zooming in into the cement phase of the concrete, we can see that we have several hydration products that are in the scale of micron or millimeters. We have crystalline materials inside there, but the most important phase inside this material is what is called the calcium silicate hydrate, which is actually the glue phase of the cement. So this has such a vague name because there is no specific stoichiometry for this phase of the cement. So as you can see here at the atomistic scale, there have been quite some efforts, simulation efforts, to figure out what is the structure of this material at the molecular level. But what I'll try to talk to you today is the in-between scale, which I call the mesoscale, or the coarse-grained scale, which is trying to figure out the amorphous and porous structure of cement paste in the submicron scale. So basically, I'll try to explain to you a model that we have come up with for calcium silicate hydrates that is based on particles. So there are indications from scattering experiments that we have a particle-based material that is around the size of few nanometers. And there are also models proposed in the past from Jennings that proposes that we have particles of 5 nanometers, that they have a complex inner structure. And these particles are agglomerated together. And we can see here from an SEM picture that this material, it has some local structure, but overall is very amorphous. So this is the goal of this modeling study, to start from particles of few nanometers, figure out the interaction between the particles and how we can produce an amorphous structure that has stabilized a porosity that is realistic for a material like cement. So as we said, again, this is our goal. We have the particles, which are called calcium silicate hydrates. We're gonna discuss what is the type of interaction potentials that we have between these particles. You can think of them also like colloidal systems, like colloidal particles, but with much stronger interactions. And then we are gonna produce a mesoscale structure. So our simulation box, it's going up to 0.5 micron. And we are going to come up with a structure which is very heterogeneous. So this structure here is composed of 500,000 particles, and the different color codes that you see, it indicates the local volume fraction inside the material. So the red regions are very dense regions, and then orange is less dense, blue, gray, and then we end up with the pore, which is basically the empty phase. But let's move back to the atomistic scale, and let's go back to where we said that this material, the calcium silicate hydrate, is a non-stoichiometric compound. So basically, we have a very nice mineral, which is called bermorite, and it has a very specific structure and a nice crystalline structure, but this is very rare. We only find it in nature, and after waiting for many years. In the cement that we usually have in our houses that is being solidified within 10 hours, we don't have a fixed stoichiometry, but we have a whole distribution of this material with different calcium over silica ratio that spans from 1 to 2.5. As I was saying, there is a lot of work done from atomistic simulations trying to understand this structure. So here, for example, you see how this material looks when we are at the tobermorite limit. So we have some crystalline layers of calcium and silicates with water and calcium ions in between. But what is actually mostly observed in the cement that we are using, it's a much more amorphous and messy structure that we see here with a much higher calcium over silica ratio. So the first goal is that we have this information from the atomistic scale. How can we devise an interaction between two grains of CSAs? So we're moving into the interactions of calcium silicate interfaces. So a way to do this is to use the potential of mean force. So here, in this simulation work from Comey and al., we have two atomistic configurations of CSAs immersed in water, and using a perturbation theory technique, we can get the thermodynamic potential as a function of the distance. So knowing this thermodynamic function, we know exactly the interaction between two particles at specific temperature and pressure. Then we can use this interaction as an input on a molecular dynamic simulation and go to the next scale, so having a coarse-grained model at the next level. Let's go a little bit deeper and understand what really is happening between these two interfaces. So they've been models already from the 90s and early 2000s that they assume two platelets of CSH. The CSH highly charged surfaces, and in between it has a solvent, which is water, and calcium ions that are neutralizing the charge of the planes. So having a primitive model here will give us the curve that we see here, which is the gray curve. So here we are measuring the pressure between these two charged planes of CSH as a function of the distance. And we see that the pressure that we observe is very low with the primitive model. The primitive model is a mean field approximation. So this is what we are expecting to get. So in a recent model that we came up with, again, with the idea of coarse graining, so here we have a system that doesn't carry all the atomistic simulation information. So we don't have all the different species, calcium, silicate, that are forming the planes. We only have two planes for the CSH with the right surface charge. And inside we have the calcium ions that are making our simulation electroneutral. The different colors here, they just are to denote the side on which the ions are. And in this type of primitive model that we propose here, we introduce an explicit solvent. So we are using explicitly the water. So if we use a hydrated ion for the calculation of the pressure, that would correspond to an ion with a larger size, we get a pressure which is different than the one we calculate without the hydrated ion, but still is not the correct for a cement. But what is making the difference is when we explicitly introduce water molecules in the simulation. When we introduce water molecules, we have an attraction which is much stronger, and it's approaching the one that we are finding on cement. So doing this addition to the primitive model, basically the explicit water, is really powerful. It allows us to recover features that usually can only access with atomistic simulations. So to give you a little bit more information on this model, we did the same calculation with different surface charges. And as we increase the surface charge, we see that we reach at some point a cohesion at the order of 6 gigapascal, which is the order that we find on cement. We can also reconcile experimental data from atomic force microscopy, where we see that the force that is measured depends on the calcium concentration and the surface charge. And we can go from a repulsive regime into an attractive regime through attractor-repulsive interactions. So this is exactly what we can get here. For example, with the low surface charge, we have a repulsive solder, an attractive well, and when we increase the surface charge, we have a very attractive well, which corresponds to the cohesion that we find on cement when we are at hardened cement base. And a little bit more insight that we got from this type of simulations is the reason why this is happening. So basically, we can see that this is due to the bound water, which is happening around the ions, as we can see here. Here, we see basically this layer, if we would remove the charged planes, so we see it from the top, and from the scattering, we can see that when we have low surface charge, the water and the ions, they can freely move in this plane, whereas when we have high surface charge, both the water and the ions are localized on the plane, and this is what is causing this very strong attraction that we have between the calcium silicate hydrates. So basically, this is a coarse-grained model that we could also think to apply it on different materials, like, for example, clays that they have with an adapted surface charge or different ions in between. But for now, staying on CSH, I'm going to move to the next step, which is how we can produce a mesoscale structure. So from this part of the interaction, we are going to keep that now we can describe these interactions with a simple Lennard-Jones-like potential, which is using different exponents here, 12 and 24. Usually it's 6 and 12, but here we have 12 and 24 to get the right well for the CSH, and we have a Yukawa potential that will create this repulsive solder. And by tuning the energy parameter of the Yukawa and the energy parameter of the Lennard-Jones, we can see how much attraction and repulsion we have in the system. So let's move to the hydration of cement. So as we said, we know the interactions between the particles. Now we need to have a simulation scheme to describe what is happening during cement hydration. So cement hydration is basically a reactive solidification. So we start with a liquid suspension. We have cement grains at the scale of microns and water. These grains start to dissolve, and once the solution is supersaturated with calcium and silicate ions, we have the precipitation of cement hydrates or calcium silicate hydrates that they grow around the grains and eventually they fill up the space. So we have a dissolution precipitation process that turns a liquid material into a stone. So here what we did is we assume that we have our simulation box between two grains of cement. So we have a pore solution which is supersaturated, and we are gonna model the precipitation of calcium silicate hydrates. To do so, we use a hybrid modeling scheme that contains a grand canonical Monte Carlo part for the addition and deletion of particles, and a molecular dynamic part where we use to for the dynamics of the system and to relax the structure. So we have a rate that controls how fast or slow hydrates precipitate, and we have the chemical potential on the probability of the grand canonical Monte Carlo that controls what is the equilibrium density of the system. So here you can see how a simulation looks like. So we don't see the spherical particles that we have. We see only lines that connect the particles. And the color coding here corresponds to the nearest neighbors. So we start from a system that has clusters that are growing on an elongated fashion. And these elongated clusters are forming a gel network. And on top of this gel network, we have the creation of a porous solid. So most of the material here, as you see, it's red, so it will be crystalline-like. This is because the simulations are done with monodispersed particles. And if we want to see a little bit more the phases we go through is happening here. So we start with the cluster phase, then we have an accelerated precipitation, the formation of a gel, and the decelerated phase where we have the desification of this gel and the creation of the porous solid. So we're able to compute the increase of the volume fraction with time and compare with the degree of hydration. And we can observe an accelerating and decelerating regime, having this typical sigmoid curve that we can see in different growth phenomena. Another point is that we can have these structures that are out of equilibrium and porous, and these structures, they can have different porosity that is controlled basically from the degree of attraction and repulsion that we have in the system. So these are two systems that are done with the same simulation protocol. They are at the same volume fraction. The only difference is that here we have an attractive well which is stronger than the repulsion. Whereas in the other case, when the repulsion is stronger, we can stabilize smaller pores in the system. So, of course, all these things have a meaning if we can validate the results we get and they are meaningful for cement. So a way to characterize the structures that we got is by getting the distribution of local volume fractions. So here you can see, for example, the local volume fraction, which the higher one is in red, which is larger than the close packing fraction, is forming this red network that is percolating inside the solid and is also bearing the load. And we see that inside this material, we have a continuous distribution of different volume fractions. So it's far, far away than being a homogeneous material, is mainly driven by heterogeneities. So one point of validation is the small angle neutron scattering. Here we see the comparison of the small angle neutron scattering signal calculated from experiments and from simulation. And we see that we have a very good agreement, and we're also able to obtain a q to the minus 3 dependence, which is very characteristic for porous material of cement. And we're able also to provide an explanation for this, which is due to the surface roughness that it's observed on this material because of particle polydispersity and because of this type of aggregation procedure, which is very fast out of equilibrium. So we have the creation of these clusters that they give different, they give a surface roughness at 2 different orders of magnitude. And next point of validation with cement was to compute the mechanics. So for example, here I give you an example of computation of the indentation modulus that we compare with experiments, and in yellow is the ones that we computed from simulations. So we're able to compare, as I said, structure with small angle neutron scattering, nano indentation, mechanics, and then next, the most important point is to compute pore size distribution. It's a key point for cement, the porosity that it has, the sizes of pores, and its connectivity. So here you can see the pore network that we get from the simulations, and here is the pore size distribution. So we have a peak of nanopores of 1, 2, 3 nanometers. These are called gel pores in the cement community, and they have been observed with NMR experiments. So on the scale of 5 to 50 nanometers, we have the capillary porosity, which has a continuous distribution of sizes with a long tail. And this is what is usually observed with nitrogen adsorption-desorption experiments. So this was another point that we could connect together with these experiments. And on the third part of this talk, I wanted to show you a coarse-grained simulation for fluid-solid interaction, all connected again with cement. So we started with this structure that I show you for cement. So this was a particle-based simulation using molecular dynamic simulations in Monte Carlo. But now we are turning this simulation into a lattice to perform classical density functional theory. So each point in the lattice is either a solid or a fluid. And we have the interaction between a node that is fluid-fluid or solid-fluid. The solid-fluid interaction, in this case, we have calibrated from atomistic simulations. And we have used 2 different fluids. The one is nitrogen, which is usually used to probe the pore space of cement. And the other is water, which is very important because there is always water left in the pore space of cement. So with this simulation, we were able to model the adsorption and desorption of cement. So here we see a slice of the system at different relative humidities of 30, 60, 90%. So we see how the water is adsorbed around the grains. And we are going through all the different regimes, pendular, funicular regime, and fully saturated. And then we have also the desorption, and we can see that at the same relative humidity, the material is adsorbing and desorbing differently the water. So this is something that we can also observe when we plot what we just saw. So we are plotting the adsorbed mass ratio with the relative humidity. For nitrogen at 77 K, this is the temperature usually where the experiments are performed, and for water at room temperature. So for nitrogen, we have an adsorption and desorption that has the same path, but for water, we have a hysteresis loop, and this is what we just saw before. So basically, with this simple mean field DFT theory, we are able to capture such a complicated phenomenon of hysteresis. But the important thing is that we need a realistic texture for cement. So we need a texture that has a pore size distribution that is realistic and connectivity of the pores that is realistic. We need to calibrate the fluid-fluid and fluid-solid interaction appropriately. And a very important point is that we need the grid size of the simulations to be nanometric. So this is the expensive part of this computation. We have a grid that is 0.3 nanometers, exactly the size of the water molecule. If the grid size is not this, we are not able to capture the simulation. So we really need to have to model the structure at this scale.
Katerina, could you wrap up?
Yes, I wrap up. So next point is that if we compare pore size distribution computed from the simulations with topological characterization and from the adsorption-desorption curves, we see that we get the same gel pore peak and capillary tail when we use nitrogen, which is not the case for water. So for example, that was a way to say that it's not appropriate to use water for such simulations. So I will wrap up here, and I'll be glad to take your questions. Thank you for your attention.
Thanks very much, Katerina. That was a really, really interesting talk. Can I ask if anyone has a question? Could you raise your hand? So if it's okay, maybe to get the ball rolling, could I ask you a question? I mean, one thing we've noticed in the soil mechanics literature, which is kind of where I live, if you like, people have started to do some coarse-grained MD, and often the number of particles in their simulations are only about 1 to 2,000. Mm-hmm. And you know, you've shown that your sample sizes are rather big, and then you talked about the heterogeneity of your system. Is this an issue for this, maybe the civil engineers using these types of numerical models, that they don't appreciate that they need to, you know, have a representative element volume, and that it can be very, very big for this type of material? Is that something you've thought about or come across?
Yeah, exactly. So it's not that we like to use all this particle. For example, when I'm talking about cement, which I know well, the experimental literature, a point why we had to use so many particles and go to so large scale is that if we want to connect with scattering experiments, we need 2 orders of magnitudes. We can see here from the signal that we have heterogeneities at 2 orders of magnitude. So if I don't have this large system, I could never compare with this experimental data. I have the beginning of this curve, but there are systems that can behave very different. After a while, they can have a plateau, or they can have another peak. To be sure that we have this exponent for 2 orders of magnitude, it was very important to go on a large scale in terms of simulations and particles. So it really depends on the system. If the system is homogeneous and it has a well-defined representative volume element, we can stay in a small system. But when we talk with systems that have so large heterogeneities, both on the scattering and on pore size distributions, in order to find pores that are so large, we need to go to system sizes that are at least 200 or 500 nanometers, starting with particles, which is only 5 nanometers.
Okay, thank you. Which, you know, I think that's something that, as I say, I'm not sure everyone really appreciates, even though it's a pretty basic thing when you think about the materials. I can see that Otello Roschioni has a question. He's raised his hand. Otello, would you like to speak? Or do you want to put your question in the chat?
Yeah, let me just ask the question quickly. Well, it was a nice talk. I was wondering, when you showed the Monte Carlo simulations of growing of cement from solution, there's formation of a crystal. So what's the potential governing the old in these simulations? Is there like an angular term or something? Or is just a pairwise Lennard-Jones type potential? So maybe I missed it.
Yeah, so it's a pairwise potential. It has a Lennard-Jones type of term with a little bit more narrow well and a repulsive term. So it's a point-to-point potential basically.
Yeah, so sorry. So is that the only potential governing the formation? Oh, fantastic.
Yes. So if you use a different type of simulation, you could do something more complicated. But here, what we wanted to do was really to stay with a simple potential that stays close to atomistic simulations and experimental data that we had. And we were able to do this with using a typical symmetric potential. So we didn't need to go for something more fancy, which was good for the simulations because they were at least light from the point of view of the interaction.
Good. Thank you so much.
You're welcome.